Okay, so this is a screencast of how I use Tracker and Logger Pro to model the motion of my mousetrap car, which I made the mousetrap car for distance. My other two partners in my group made the other two mousetraps, and so pretty much I imported the video, and then I used a calibration stick and I measured the distance or the width of my tile from the middle of the little square thing to the very end of the first tile, and it was about 0.5 meters. So I set the calibration stick to that, and then I created my grid, and then created a point mass, and then tracked it. And so you can see how most of the data was pretty good. The last part got a little iffy, but it's still workable. So that's how I use Tracker, and then I just copy pasted all of this onto Logger Pro here, so I can show you that right here. So all I did was I deleted the Y. I unchecked the box because I don't really need the Y. I'm just doing position time, and then I just copied all the values for position time, then put them into Logger Pro here, and then to get this velocity column, I created a new calculated column right here, and then I took the derivative of position, because derivative just means slope of, and so the slope of the position time is it's our velocity. So as you can see, derivative of the position time, and then I got my velocity values, and then the bottom graph I graphed velocity versus time, and the top graph I graphed position versus time. And now I saw that like the first part of my position time graph was like an upward curve, and so that told me that because the slopes at each point they're getting steeper, that told me that my mousetrap car was speeding up in the beginning, up until like about 1.5-ish seconds. Then after that it started slowing down, because you can see like the next part of the graph right here, from here to here, towards like the end almost, the slopes are getting smaller as we go in time. So the data is not as good as the first part, but still you can still tell that the slopes are getting smaller, which means that my car was slowing down. And so then in the velocity time graphs, the beginning part here, I knew that was the velocity for when my car was speeding up, and the reason why I know that is because all the values for velocity are positive, and the slope for the velocity is also positive. As you can see here, slope is 0.9553 meters per second squared. And so that's when both the velocity and the slope of velocity, which is acceleration, when they're both the same sign, which is positive, that means that the car would be speeding up. And then down here, the second part of the graph here, I knew that my car was speeding down. This was the velocity for when the car was slowing down, not speeding down, because the values for most of the velocities are positive, but as you can see, the slope for this part of the velocity graph is negative, which means that because the velocity and the slope of velocity, which is again acceleration, because they're different signs, the car must have been slowing down. So that was how I knew that my car first was speeding up and then it was slowing down. And then next, I analyzed the velocity slopes for when the car was speeding up and when it was slowing down. And for when it was speeding up, the slope of the velocity, or the acceleration of my car, was about 0.956 meters per second squared, which means that every second the car was speeding up, was going 0.956 meters per second faster. So that's the acceleration. So and then for the second part, I analyzed the slope of the velocity when the car was slowing down, and I saw that the slope of the velocity, which is the acceleration, was negative 2.262 meters per second squared, which means that every second the car was slowing down about negative 2.26, sorry. So it was slowing down about negative 2.26 it was going slower at that rate. So again, the acceleration is negative 2.26, and which means that when the car was slowing down, it was slowing down by about negative 2.26 meters per second every second. And that's the acceleration. And then what I did here is I kind of wanted to see how well my data fit in like the real, or the data I collected, how well that fit the numbers I got here. So I did analyze, and I analyzed the model. And for the first part of my graph here, the part where it was increasing, oh yes, and we know that the position is always quadratic, so I picked the second one. And so the A, I knew that the A would just be half my slope, because and so I took the slope and I divided it by half, and I can show it here. No, I can't. But so here, 1 second. Model. Yes. So my A was and I'm doing this for the first part of my velocity graph, which is when the car was speeding up. So half of 0.9553 is about 0.47765. So 0.47765. And then my B, which is just my initial velocity, which is also the y-intercept of my velocity time, was about negative 0.5310, so negative 0.5310. And then my C, I had to kind of play with to see, to bring it down. So that's a little too big. So I'm going to do like 0.9. That's too big. So yeah, so as you can see, I kind of just played around with it, and it models it pretty well actually. Here, maybe I can even try to make it better. Yeah, see, so I already did it on the graph, but I just wanted to explain how I got, this, how I modeled it. So that's pretty much what I did, and I pressed OK. I'm not going to do it because I already have it here, but as you can see, it's a pretty close fit. And then I did the same thing for the part where the graph was slowing down, or where the car was slowing down. So I did, where is my model? And then, so I did the same exact thing. So we know that it's 1/2 AT squared. So here, no, it's just that. And so I know my A is just going to be, again, this time it's going to be, because I'm trying to model the part where the car is slowing down, I'm going to use the data for the velocity time graph when the car is slowing down, or the car. So my A, in this case my slope, is negative 2.262. So I divide that by 2, which is about negative 1.31, so negative 1.31. I entered that, and then my B was just my slope, which was 4.09, and then my C is just, I'm gonna have to play with that, so I bring it down a little bit. That's gonna be a lot, so let me try like negative 2. Okay, negative 3. Okay. There, I typed it in wrong, that's why it wasn't working. There we go. And then, so if I mess with it a little, 5. So you can see it's still a pretty good fit. And again, I'm not going to press OK because I have it done here. I just want to explain how I got that. So in both cases, it's a pretty good fit, which just is, I mean, it's good enough considering that this was data collected in the real world, and there was probably a lot of error. So just a quick review. what I did essentially here was I kind of find the equation for the position time graphs too, and so the part for where the car is speeding up till here, so this entire part, the equation for that curve is 0.4777 t squared plus or minus 0.5310 t plus 0.25. So that would give me, that equation would model the motion of the car when it was speeding up, my mousetrap car. And then the second part, which kind of starts here, where the car was slowing down, the equation for that would be negative 1.131 t squared plus 4.093 minus 3.056. And that equation would equals x. And that equation would obviously model the motion of my mousetrap car when it was slowing down. So a real quick review. I explained the accelerations, they were just the slope, and so actually we can calculate displacement in this case. Okay, so we can calculate the displacement of the mousetrap car, and so how we do that is we just take the area under the velocity time graph, and so I found the points of intersection. So for this first velocity line, I found the y-intercept, which is here, which would actually be the height. The y-intercept is negative 0.5310, and I got that by just looking here, y-intercept. Then I got the x-intercept of that graph by setting the equation of this velocity graph equal to 0. So I set that equal to 0, and I found that this point here is 0.556, and then so I use that to calculate the area under this graph, which is just 1/2 times base, which is 0.556, times the height, which is negative 0.5310, which would give me negative 0.148. Negative 0.148. So that's the area of this graph, of this little part right here. Then I found the area under this entire thing by finding the so I found this point. This point here was 0.556, which was the 0 of the first of this velocity time graph, the x-intercept, and then this I found the x-intercept of the second velocity time equation, and that was 1.809, and I subtracted that 1.809 by 0.556 to get the base here. So I got 0.5249, and I multiplied by the height here, which I found by just finding the maximum height up there. So because that's approximately the height, I found that to be 0.8536. Then I multiplied, so I did 1/2 base, which is 0.5249, times height, which is 0.8536, and I got 0.224. And then I did the same thing for the last part. Because my data kind of ended here, it's kind of where I went up to, so I subtracted this x-intercept, which I previously said was 1.809, from 2, and then I got, so the base of this triangle would then be 0.191, and the height of this triangle I found to be negative 0.431, and so I did that by just plugging in 2 into the velocity time equation for this one. So the area under that part of the triangle is 0.5 times 0.191 times negative 0.431, and I got negative 0.0411. So if I add up those three, so negative 0.148 plus 0.224 plus negative 0.041, I will get 0.035. So my car traveled approximately 0.035 meters. That was how much it traveled. And so that's it for this screencast.